let's run through my solutions to the Introduction to Vectors worksheet. I think everyone I saw had these answers for the sums and the differences of vectors, but one thing I want to point out is that vector addition is commutative just like real numbers. And to say it's commutative means it doesn't matter the order in which we the order in which we add the vectors. So here we've got this sum v plus u. We travel along v, and then we put the tail of u there and travel along u, and then the resulting vector is v plus u. We could do the same traveling along the u vector first, and then traveling along the v vector, and you see that the result from the very start to the end is the same, this vector v plus u. In terms of multiplying, scaling that is, we can multiply a vector by a real number, which has the effect of stretching or compressing it. As I wrote here, when we scale a vector, the magnitude changes, but the direction does not, with the exception that if we scale by a negative number, it might flip to the 180 degrees direction. I think everyone did pretty well with these, breaking them down in terms of I and j. If you know the I-j decomposition of a vector, then we can just use the Pythagorean theorem, which looks a lot like the distance formula in 2D, to find the lengths of these vectors. And then using this bracket notation makes it a little more convenient to do things like adding and subtracting vectors. So as you see here, we can add a pair of vectors in their bracket notation just by adding the first components, the x or the I components, and then adding the second components together. Likewise, we can scale vectors by almost like distributing, multiplying our scalar times the first component, and also our scalar times the second component. And then to talk about the length of a vector given in bracket notation, we just use the Pythagorean theorem. So a term that I'll use a lot here is component-wise. That is, vector addition happens component-wise. We add the first component to the first component, we add the second to the second, and so on. Subtraction works the same. We add the first, or we subtract the first and the second. And the same is true for scalar multiplication. We scale both components of the vector. So on to number 6. Is 4, 6 a vector that's parallel to u, the vector 6, 8? And no, it's not hard to see why you can't scale 4, 6 to get to 6, 8. If you remember, we need to scale both components by the same real number. And the last question, part B, is how can we find a vector that's parallel to u? Remember, u is the vector from up here, 1, 1, but that has a length of 2. So earlier we found that the vector u has a length of root 2. So what I did is I multiplied by 2 over root 2 to get a new vector, and I check here that that works. We'll talk a little bit more about that in the next video, where I talk about some of the basics of vector arithmetic.